About cracking a short RSA key. Now here's how you generate an RSA key. You want to create a public key, which is N and E, which we talked about last time, and a private key. So you choose two large primes. Then you multiply them together to create N. Then you compute phi of N, which is P minus 1 times Q minus 1. And then you select a public exponent, which has this mathematical property, but in practice you almost always use 65537. That is the standard number everybody uses, although 3 and 5 would work too. For some reason the standard most people use is 65537 for E, and then you find D, so that's the inverse of E, mod phi. So multiplying them will give you a 1 mod phi. So here's the problem statement. I have Megan's public key, and I'm going to try to find her private key. And that should be impossible, and it would be impossible if the N and Q, if the P and Q were big enough, but this is not big enough. As we talked about before, the current recommendation is at least 2048 bits, maybe 3,000 or so bits. And this is not that many at all. This is about 20 digits, about 60 bits. So that's why it's going to be, in principle, crackable. So we're going to crack it. And so we have to have PyCryptoDome, which I've already done on this machine, I'm pretty sure. And we'll find out. I'm going to do Python 3. And then I import math, and I try to do the square root of that number, because I want to find out what P and Q are. So what I'm going to do is start from the square root. If there's a square of a number, it would be there, and then I can work from there. One number P must be lower than that, and Q must be higher than that. By tradition, you make the smaller of the two P. So I'll be in the right range if I get to the square root. So when I calculate the square root, you can see I'm getting a strange number with fraction on it. All right, but that gets me close. So this number here, 10, 100, 711, 415, is more or less the square root. So what I'm going to do is, I know one prime number must be a factor less than this, and one must be greater than this. Prime numbers have to be odd, so the first candidate is 413. And then I'm going to go down, jumping by -2 every time. I know this P must be 413 or some odd number below that. So I'm just going to start there and go down. I'm going to try going down 40. And I'm just going to print the I, my guess for P, and then n% I, because that's the modulus, and n% I will be 0 if it divides evenly. So I will try 40 numbers here, starting at the square root. And there we go. And right there, I get a 0. So that is P. So what we have here is a fairly common way people make problems you can solve with RSA. If you move P and Q are near each other, then it's easy to solve. And if P is only like about 5 or 7 below the square root, then Q is just going to be 5 or 7 above the square root. So I found them both. And one extreme case is companion primes. There are primes that are only 2 apart, like 5 and 7 are both prime. And 11 and 13 are both prime. And that happens all the way up. You can find companion primes that are only different by 2. Now this looks like they're different by a little more than that, but not much more. So the third candidate is the winner. That number ending in 9 is P, so we can calculate Q. We know P, so Q is just N over P. And now we can do various calculations just to verify that everything is right. We're not being fooled by some kind of round off. Here's P, there's Q, and to test it, I'm going to take P, Q, and N, which we knew before, and then P times Q. So there's P times Q. This is N, that's P times Q, and here's N minus P times Q. It's really 0. So it's not a mistake caused by a round off error or anything. We have found P and Q from N, so now we can find D. You take phi, which is P minus 1 times Q minus 1. All right, and there you have it. It's this long number. Now we have to find a D with this property. D times E mod N mod phi is 1. Now there is a simple way to do it in Python. The PyCryptoDome library, there's a thing called Euler's algorithm, which will quickly converge to this number, and somebody else has already coded it for us. They've created this thing called inverse, which does the modular inverse of a number. So all you have to do is the inverse of E modulus phi. You just have to import that function. So I'm going to use 5 for E. Like I say, 5 is one of the common numbers people use for this. I'm just going to use the algorithm somebody else wrote. It imported, well, because I imported Cryptodome. PyCryptodome contained this inverse function, and so I can now get D. That's the decryption key. Notice the encryption key is 5. The decryption key is this huge thing. That's what happens. The two of them multiplied together have to be 5. So by choosing E small, you know D is going to be big. And that's intentional. So encryption is fast and decryption is slow, because you're thinking about logging in, encrypting on something like a cell phone, and decrypting on a server. So you want to make the job of the client easy. And you're willing to sacrifice making the server work harder because it's a big, powerful machine. That's the game. So now we can encrypt a message. What was the problem statement? Find her private key. Well, we did that. And now we're just going to try encrypting a message. Okay, so we're going to send a message hi by just taking each letter and turning it into a number. And then what I'm going to do is combine it all to one big number. This is a more realistic way to encode data than what we did last time, where we encrypted the bytes one by one. I'm going to turn each byte into a number. So HI exclamation point will turn into that. Then I'm going to just take each byte and line it up in a number. So take the first byte and 256 times this byte and 256 squared times that byte. So in hex, this is just making a long number. So if I in fact print hex of X, then this is 48 is ASCII for H, 69 is ASCII for I, and 21 is ASCII for exclamation point. That's why I encoded it this way. It's just standard hex encoding, turning this number into base 10. So that number encodes this message. And now I can encrypt it by taking x to the e mod n, and I can just do that the simplest way here, x to the e mod n. You can get away with this for small numbers. For larger numbers, you have to use the mod pow function, which is faster. But this is going to take x to the e mod n, and there it is. It's that number. That is the encrypted version of this message. That's longer than number 247. So you could send that safely over an unsecure channel, and nobody can get in unless they know Megan's private key, although the public key in this case is so short that, as we saw, people can hack in. So we'll decrypt it with y to the d mod n. So we can take XX, our proposed plain text. In general, y is the ciphertext and x is the plain text. That's standard notation. So this is XX is my decrypted stuff, which is y, the encrypted stuff, to the d mod n. And it freezes because now I'm taking this huge number to this huge power. And if I do it this way, it's going to do repeated multiplication or something that's going to take forever. So you have to use a faster routine, and that is this one, the pow function. The pow will take y to the d mod n. And up here, I didn't, and so up here it tried to calculate y to the d first, creating an unthinkably huge number, and then do mod n. Here it's going to use the fact that it's modulus n to speed up each step of this calculation, and it will become much, much faster. So that's why I use a smarter power function, and it'll go much faster by exploiting the fact that it's modular, so it doesn't take any time at all. And now I get back to my original x, and I could say I could just decrypt it. One simple way is just doing this. Now I can read the values, 48, 69, 21. They're just ASCII values. You could look them up in an ASCII table. So if I look, put that table up there and I bring my, all right. So this is 48 is capital H, 69 is lowercase I, and 21 is exclamation point. So that's why I did it that way. And I think I have a mathematical way to decrypt it here. Yeah, here you take the integer. This will give you the higher order byte. This will give you the next byte, and that'll give you the next byte. This will invert them. This is the mathematical way to turn it back into plain text rather than looking it up on that table. It amounts to the same thing. You get hi. All right, so that's the game. And so then you just have a couple flags here. Use the same key and encrypt a different message. Encrypt a different message using the same key. And now here's a different public key, and Megan sends a message, and you have to reduce this to P and Q, find 5, find D, and then decrypt that. And here's a much longer version, and you'll have to use a better calculation to get your square root in the right area, and then try to guess keys near the P and Q, and they're near there, but they're not as close as the last one. So there's just a few challenges. So that's an intermediate level of RSA. Last time we did RSA with ridiculously small P and Q. Here we're doing it with larger P and Q, not large enough to be secure. Later on we'll do it with actually modern P and Q that are bigger calculations. So stop this one.